And the last topic of this unit is on Bayesian inference with continuous priors. We're going to cover like Bayesian hypothesis testing and Bayesian credible interval. That's also similar to a confidence interval but different interpretation. And lastly, how to do Bayesian prediction. And so those are the things that we cover. So one type of question, if you're doing hypothesis testing, will be, suppose one of the Tokyo Express's workers claims that at least 70% of the customers prefer Friday. You're wondering whether this is a reasonable claim. So this is directly talking about the probability of P, right? And then given our data and then as the priors, we came to this point of the beta posterior distribution, and then we can directly test this in a sense that we can look at how likely it is for P to be greater or equal to 75%. Okay? So you can find the posterior probability that this particular event P is greater or equal to 0.75, and then you can make the decision on the value of this posterior probability. If it's going to be small, we can reject. If it's going to be large, we do not reject. Okay? So one way you can do this is through the prop-based package that I mentioned before. So this is the beta underscore area function that can do that for you. So this is the R script that you do it. So pretty much you have to fit what is the lower cutting point, which is because we want to get greater or equal to 75%, right? So you set the LO, stands for low, to be 75% high, because it's proportion, so it goes from 0 to 1, so the maximum number is 1, right? And then you input the shape parameters. So remember, these are the two shape parameters in the posterior distribution of P. Okay, so you input those two. This is really just setting the color of what is going to show up, so it doesn't matter. And this line in here is just trying to get the size, the text size a little bit larger, so it's easier to read. Okay? So you can see that by running this function, we're looking for this portion of the probability, and then because again it's a proper distribution, so the area under the curve, the whole curve is going to be 1, right? So we're exactly looking for the shaded area, and the probability once you run this function, you will see that it's going to be show up for you on the top. It's pretty small, 4%, so you can reject the claim. And I'm hoping you brought your laptop today with you, so let's just to get us all started using the package and everything. So I might have to do a little demo of how to install the package on the board on the screen. So, so the question now is, most 30% of the customers prefer Friday, so we need to find out the beta area of P smaller or equal to 30%. So let's see. Let me stop share here, and I will go to my thing. And what we can do is, okay, so first of all, I need to demo how to install the prop-based package. Let me see. So on your computer, so it's in RStudio, and what you do, okay, so where did I save this? I think, so we need a package called dev tools. So what you do is you first of all install that package, EEV TOOLS.
Could you repeat that over?
Yes, let me actually just, I just did something not recommended. Okay, yeah, so you should install yeah, I think because it's running, so it's not. Let me actually blow this up a little bit so it's easier to read. Yep. And then you load this library. It might take a while, like here, 6 times to run it. So we'll load that. And then once you have it, dev tools, column, and then install. Yeah, it's not giving me the auto fit, so I don't remember. Just give me a second.
Yeah, I just made them. Wait, I made like a prescription. She's on the you don't need to, but it's just like you. No, she's not. She's submitting a score. Oh, for yeah. Okay.
Yeah, it's a bit slow on my end, so this should be the right code. And I was just hoping to demo this here. Yeah, Kat? Huh?
Yeah,
Sure. You mean like even bigger?
Yeah.
Yeah, okay. Yeah, let me try to, I thought I can do, yes, okay. So this is still running, right? Yeah, so this should be the entire 3 lines that you need. Okay, so maybe the last thing is to load this package across the base. So I might have to wait a little bit here just because it's slow on the server, but it's probably pretty straightforward on your computer. So let me just, well, did you get it?
I don't have internet connections on research.
Oh, all right, okay. Anybody, so anybody found any problem with the code that I wrote?
I don't have. There's no package.
Yeah, right. So that's because, okay, yeah, so you have to, let me just say here. Okay, I noticed some of the error messages saying that this is not being installed. So that's because you have to run these 2 lines first. Yeah. So, okay, install.packages and then parentheses quotes with the name of the package is just to install it. And then the library, this command is trying to load the package in the working directory. Work environment, I should say. And then line 4 here is to install the prod-based package from GitHub. And then line 5 is to load that package. So if you see any error messages of saying like, I cannot find this package, that's because it was not properly installed. So just go to the corresponding line to do that.
Oh, I just did.
Yeah, so in order to, so I will keep walking around to answer questions. For those of you who already did it, it was the data area function. So what we did in the demo just now, I think, is trying to use the, let's see, low is 0.75, right? High is 1.0, and the shape val is, I forgot exactly. Anybody remember 15.06? Thank you. And then 10 point something, right? Is that right?
Try to pull up the modal.
You're right. 10.50.
Thank you. And so these are, yeah, I think actually just running this should be fine. So that will get you the 4% that we showed earlier on the slide. So this is, for those of you already installed and then load the 2 packages, you should be able to run this. And the question for you, that exercise is, what is the probability that, what is it, at most 30% of the customer
Did you run the sign library?
prefer Friday? So let me keep walking around to answer questions. So it's shaped R, not shaped bar here. So once you have the correct thing, you should be able to run. All right, so yeah, so if you see here, I think I have downloaded, installed. Okay, so this is fine. And this is installing. Okay, this might take another time, I don't know. But anyway, so for most of you, it should be working. And once you have done it, you will be, you load the library of prod-base, and then you run line 7 here. You should be able to get the 4% that we saw earlier. And then to answer this question, we can use beta area. And then what would be my low and what would be my high this time? If I want to find that at most 30% of the customers prefer Friday. Yeah.
0 and 0.3.
Yeah, so if I said 0 for my low, high to be 0.3. Oh, stop. Okay. So let me make sure. Okay, it's running now. Yeah, so this is the 4% I was talking about earlier. And now we're trying to round the other one. So shapes are the same, two shape parameters. And then if you run that, also going to give you, so it's going to be super small, right? 0.001 here. So it's really low here, around like 25 over here. So this will be how you can answer the question that I posted earlier. And this is examples of doing Bayesian hypothesis testing using the beta underscore area function. Okay. But in this course, we also cover how to do Bayesian inference using simulation. So let me go to here. Some of you have the slides ready, so you can look at the next slide that we are using the R beta function to generate random draws from a particular beta distribution. So, oh yeah, go ahead.
How do we get the 15.06 and 10.56 in the data?
Right, okay, yeah, so that was before, so let me,
Oh.
yeah, so, okay, so those two numbers, yeah, again, it's, they came from the previous discussion about how to derive the posterior. So that was the A plus Y, and then M plus, B plus M minus Y, yeah. Great, okay, so, so again, when you do hypothesis testing, the beta underscore area function in the prop-based package, it is giving you the exact solution. That's in a particular package, but you can also use the standard R function like P beta here. So P beta is getting the percentile. So what you do is you evaluate P beta at 1 and then at 0.75, and then of course the second two inputs are the shape parameters that you needed. So you can see that it gets pretty close to 0.04. So I mean, this is probably more detailed solution, and then what's in the beta area function that we saw earlier was rounded up a little bit. Okay, so this is when you know the exact posterior distribution, which is beta 15.06 and then 10.56, and then you use the exact solution, either beta area or our P beta function. The other methods that I want to cover is to use what we call Monte Carlo simulation. So this is in the book is on chapter 4, but we're reading into the topic itself. Now you can use what we call the R beta function. So R stands for random. So R beta is taking random draws of the beta distribution. Okay? So the example that I gave you here is you set capital S to be number of draws that you want to do. For the demonstration purpose, I'm doing 1,000 draws. And then I create like a variable here storing all of the R beta samples I'm generating. So I'm using R beta function here. The first input is S, that's the number of draws that you want. And the second two inputs here are the shape parameters. Okay. So once you run this, you have 1,000 beta samples from this given beta posterior distribution. Okay? And then in order to compute the probability that greater or equal to 75%, what we do is we have this greater or equal to sign here. That's a logical operator. We're just returning true or false of whether each draw is greater or equal to 0.75. Okay? And we sum them up. So remember, it's logical, so it's either 0 or 1. So when we sum up this particular vector, what we get is going to be the total number of 1. Okay? So that's counting the total number of samples that is greater or equal to 0.75. And then to get approximated probability, we divide it by the number of samples that we have. Okay? So this is what we mean by Monte Carlo simulation. And again, it is approximation. It's not exact solution. So if you look at the outcome that we have here, 0.037 with slightly lower, and you might, so if you want to get even more accurate result, you can increase the number of simulations that you do. So if you want to give it a try, you can change 1,000 to be 10,000. It's gonna get even closer to that 0.03973022. So this is using the R beta function, and then make sure that you know why we're doing the sum in this case. Okay, make sense? Okay, so that's for Bayesian hypothesis testing. Another type of inference that we do is creating credible intervals. So this is probably the first time you heard this term, credible interval. So it is an interval that we're confident will contain this unknown parameter. We call it credible interval because it's exactly talking about the probability. Like say if I want a 90% credible interval, it is an interval that contains 90% of the posterior probability. Okay? We try to differentiate this with the confidence interval in the frequentist method because again, remember in the introduction that we did, confidence interval should really be understood in the way that if you were to repeat this process for a large number of times, then 95% of the time that the confidence interval is going to cover the truth. Okay? Whereas here, we're directly talking about probability statement. We're saying that we're 90% confident or with 90% posterior probability, this interval is going to contain the truth. Okay? All right. So what you can do, again, for exact solution, the prop-based function has this has this beta underscore interval function. I think I showed you earlier before. And so what you can do is you specify the credible level that you're doing. So this demonstration is doing 0.9. And then again, you input the two shape parameters. The rest is about like the cosmetics of the plot, so you don't have to worry about it now. And once you run this, you can see that it gives you the 90% credible interval on the top. So it's 0.427 to 0.741. Okay? One thing about this beta interval function is that it is written to return a middle 90% or 95%, like middle certain percent credible interval. Okay? Middle meaning that we're left with 5% on the left and 5% on the right. We're looking at the middle 90%. Okay? So that's important to note because sometimes you might not want the middle one. You might want, like, say, to the left or to the right. Then the beta interval function will work for you, but you can always go back to the basic R function to do that. So before we get there, maybe just quickly do a 98% credible interval for P. What do you need to change, and then what is your answer here? Okay, so if you're doing this in your computer, you're going to change this 0.9 to 0.98, right? Anybody got an answer to share? The confidence interval, so you should read on the top of what will be the 98%. Yeah.
0.361, between 0.361 and 0.795 exclusive.
Make sense? Yeah, the same? Okay, good. Yeah, so this is how you can use the beta interval function to do this. And now let's also cover how to use the basic R function, which is Q beta. Okay, so that's talking about function here. So in order to get the middle 90%, what we need is we specify at the 5% level, or I would say level 5% cutoff point, and then 95% cutoff point, so we get the middle 90%. Okay, so use the Q beta function, and then the next two inputs, again, the shape parameters. So earlier I was saying that, and you can see the results here, pretty close to what we saw earlier using the beta underscore interval function. So again, I highlighted here that if you're using the beta underscore interval function, it only gives you the middle 90%. But if you use the basic R Q beta function, you can specify it doesn't have to be the middle, okay? If you want only the thing to the left, then you can, instead of doing 0.05 and 0.95 here, you only return at 0.9, and then that interval goes from 0 to that number. Yeah. And then of course, you can always do this using a approximation method through Monte Carlo simulation. So what we do again is we use the R beta function. Very similar. You set up the S, that's the number of draws that you want. You again save them into a vector. So this is exactly what we saw earlier. And earlier for Bayesian hypothesis testing, we're just like summing a logical operator after the vector. Here, we want to get the quantile, so you can use the quantile function. And then what you do is you input the vector name that you saved all of your draws, and then you return the quantile at the 5% and 95%. So that gives you the middle 90% credible interval based on simulation. Okay? So simulation-wise is, I mean, the lower cutoff point is a little bit smaller than what the theoretical result is. But again, if you increase the number of draws that you have, you will get a closer result, a closer approximation to the analytic solution. Make sense? Okay. All right. So that's for credible intervals. And the last topic here is Bayesian prediction. Suppose the Tokyo Express owner gives out another survey. So here I'm just using N, just in case the survey size is going to be different from what we have. Earlier was N, and now we're giving another survey to N customers. How many would prefer Friday? So the predictive distribution, so we use tilde on top of the random variable to represent it's a prediction. So we want a prediction distribution, predictive distribution, given the data that we have. So this is, given that earlier we observed 12 successes out of 20 trials, if I'm going to generate a new white tilde, what the distribution will be. So you should follow this particular format. The exact solution, which we won't cover in detail in class, it's going to be a beta binomial distribution. Yeah, this is a new distribution, okay? And it has 3 different inputs here. But for our focus, especially not only today, but later in the semester, we always want to use approximation and simulation for doing hypothesis testing and others. For prediction as well. Now, in order to do prediction through simulation, what we do is, remember, we already know the posterior distribution of P, right? So you can sample a value of P from the beta posterior that we have. And then you sample a new prediction, which is white tilde that we use here, using the P value that you sampled just now, and also the N, which is the size of the new survey that you're doing. Okay, so this is the general procedure. You sample the parameter, and then you sample a prediction. Okay? And that really just goes back to the sampling distribution. Remember, the sampling distribution is a binomial, right? We know that given the P, which is the success probability, we generate Y from a binomial distribution. So how you can do this, I'm going to pause here for a little bit, is that you set up S, you set up A, you set up B, you set up N, set up Y. And here, for simplicity, I'm just assuming that it's going to be given to another 20 customers. Okay, so I set my M to be 20 as well. And specifically, I generate a vector of P first. So that was our beta. Remember, we have this, and then this is the posterior 2 shape parameters here. And then from each of the P value that I generated, I do a R by norm. So R by norm, remember, we saw it before. I think we saw a D by norm, because at that time we were trying to just estimate the density of the binomial. But now we're generating random draw of the binomial. So what we do is, we have S, which is the number of draws that we're going to make. N is the number of trials that we have, which is the size of the new survey, right? So it's going to be N. And then you input the vector of P here. So you notice that R is working with vectors pretty smoothly, right? We generate this, which is a vector of all of the draws of P. And then you can actually directly work with vector to generate a vector of the simulated Y. Okay? So that's why you have both as here. You can write a loop, but that would just take longer. I mean, for simple cases like this, it's fine. But R does work with vectors, so it's pretty straightforward. And in the end, you can, well, for example, if you want to know that what is the probability that a predicted number of successes will be between 5 and 15, then you take the sum of two logical operators and then divide it by the number of simulations that you do. Okay, so in this case, it's going to be pretty likely, 90% chance that you're going to have a predicted number of people choosing or preferring Friday with 90% chance to be between 5 and 15. Okay. Yeah. So this is for Bayesian predictions, and make sure that you know the logic here, that we generate a random sample of the unknown parameter first, and then we generate a new draw of the data given the sampling distribution, which is the binomial. Okay. And here the plot is just showing you the exact solution. So we didn't cover how to sample it, don't worry about it. So the exact, remember, is a data binomial distribution. Okay, we plot it on the top. The simulated is on the bottom. So slightly shifted to the left, I would say, of the simulated. But I'm guessing if you have larger S, which is the number of draws that you do, you're gonna get better approximation to the exact solution. Yeah, by the way, all of this, yeah, like the plot, I posted another, like, I think our markdown file on Moodle that includes all of the script of what we use in class. So you can see exactly how I did. I included them in the R script, and then you can replicate all of the results using that file. Okay, if you're ever curious about how to make a certain plot. Last thing here is we not only make prediction, but we also try to use prediction to see how good our model is doing. So remember, on the top, we have how to do a prediction using Monte Carlo approximation, right? You sample the unknown, and then you sample a new observation. What we can do, furthermore, is to do what we call posterior predictive checking. So let me explain that to you first, and then show you how that can be done. So sometimes we make new prediction and then check our original observation against the prediction to see how well our model is doing. Okay, so this is the purpose of doing posterior predictive checking. So procedure is you start, so again, we have large number of simulations that we do. I use capital S to denote that. And what you do is you sample a P from its posterior, and then you sample a new Y. And notice that here I use M. So whenever we're using posterior predictive checking, we're going to replicate the exact same size as the original distribution. Okay? So we started with M, which is 20. So every time we generate number of successes, which is Y tilde, from a binomial with 20 trials, right? And then with the newly drawn P draw from this posterior. Okay, so you do that for a large number of times, which is capital S here. And then the sample of this Y tilde is an approximation to the posterior predicted distribution that can be used for model checking. Make sense? Yeah. So here we get S number of P's, and then we get S number of Y tildes, and then the sequence of Y tilde is an approximation to the posterior predictive distribution. Okay? Keep in mind that whenever you're doing those checking, you have to have the same size as the original data point. All right, so to do this, it's probably easier to write a loop in this case, just to see how things are done. So the first few lines, again, is still trying to define those numbers S, A, B, and Y. And we also created a data frame called new Y because we want to report them. And what I did is I put it as a data frame, and then it's S number of NAs. And we give the name of that column to be Y. So that's this two line is doing. And in order to generate predictive posterior checking, what we do is you can write a loop here. So pretty much each time you generate a P, so that was the P from data A plus Y, and then B plus N minus Y, that was that step over here. And then this step is generating a new tilde, given the P, from the sampling distribution, which is binomial and P. Okay. Yeah, so you generate one of them because we're writing a loop, we're doing it one by one. And then N is the number of trials that you do, and the set P sim is the draw that you did before. And we save it into the new Y data frame that we have. Okay. So once you run this loop, you get a new Y data frame that is recording all of the predicted samples or the predicted number of successes that you have from your model. Okay. So keep that in mind, you can try that out. And most importantly, we want to plot it in a sense that we can see how likely our data point is. So you can see that the histogram is on the predictive draws. So that was the new Y. So the histogram is on top, is applied to this. But the red dot here is 12, which is what we see in the data. Okay. So the goal of doing this is you want to see that, well, our original sample tells us 12 successes out of 20 trials. So I want to see how likely it is or how unlikely it is according to the distributed, like the predictive distribution that we have. Okay. So in this case, it's right in the middle, right? Meaning that the model is most likely in accordance with the data because it's like, say, the predicted distribution is very similar to what we would have with the original data. So that's typically done. Sometimes you might see, let me just give you an example. Sometimes if you see like the original data is super extreme, like this or like that, they might indicate that the model is not really good in a sense that my predicted values from the model is very far from what I saw in my data. And then that gives you an indication that the model is not doing well. Okay. Formally, you can also just return like checking how many are greater or how many are smaller than the predicted value. If either the probability is very small, it suggests the model does not describe it very well. So what we can do for this example is you can check how many new Y is greater than the original data 12, which is 40%, 41%. And then 1 minus that is close to 60%. So either of them is small. That means the model describes Y pretty well. Okay. Yeah. So this is typical procedure of doing posterior predictive checking. And so with all of this in mind, I guess it will be good just to recap and then work on lab 1 for a little bit. So for Bayesian inference procedure, we have 3 steps: prior, data likelihood, and the Bayes rule to get the posterior. Okay, so we have seen the whole process using the proportion example. For the proportion example, we focused on the beta distribution because they are conjugate prior, so they're easy to work with. So you start with prior beta AB. The sampling density is binomial NP, and then you come to the posterior distribution, beta A plus Y, and then B plus N minus Y. And in particular, we covered 3 or 4, I would say, Bayesian inferences, hypothesis testing, credible intervals, predictions, and posterior predictive checking. And most importantly here, keep in mind that almost all of them, we covered the exact solution versus the simulated solution. Okay. Later on in the course, you will see that we're going to focus more on the simulated because in a lot of cases there are no exact solution available, so we'll have to use numerical methods to approximate them, and that's for this whole unit on proportion. Any questions? Okay. All right. So probably a good time just to go to work on lab 1.